In this video, we're going to talk about the graphs of cosecant and secant. First of all, I want to remind you that cosecant and secant are reciprocal functions. So specifically, cosecant is the reciprocal of sine. Now, reciprocal is not the same as inverse. So we'll talk about inverses later, but we're just talking about a reciprocal for now. So if our fraction is sine of x over 1, if I flip that and take its reciprocal, I get 1 over sine of x, which gives me the function cosecant. So that's just a reminder. We know this, not brand new information. So there's a couple of things that happen to the graphs of both of these functions. So here we have the green curve, which is sine. It's this constant connected function that doesn't have any gaps or asymptotes in it. But there are values on the unit circle where sine is 0. And if we were to take cosecant of that same angle, we'd get 1 over 0. And so that means that there must be asymptotes somewhere along cosecant. And there are plenty. And they repeat every pi. So 2 places on the unit circle, technically 3. Sine is 0, at pi, and at 2 pi, which is the same as 0. But so that's going to repeat every pi. So that means that there's going to be an asymptote for cosecant at every pi. So at 0, at pi, at 2 pi, at negative pi, negative 2 pi, etc., on forever and ever. And so when you take the values of sine that do exist, that are not 0, and you flip them so it becomes 1 over whatever that is, it actually flips your function up like this. So wherever there's a maximum point, it flips it up to be kind of what I think of as like a smiley face. And then when you have a minimum on the sine graph, it produces a frowny face. And now here we have secant, and of course that's the reciprocal of cosine. So just like cosecant, which was 1 over sine, we have secant as 1 over cosine of x. And there are places on the unit circle where cosine of x is equal to 0. So therefore, secant will also have asymptotes at those places. So the green curve here represents cosine, and the blue curves are secant. So much like cosecant has asymptotes and kind of like rebounds off of the max and min points of sine, same thing happens with secant. So the asymptotes where cosine is equal to 0 happens at pi over 2 and 3 pi over 2. So 90 degrees to 70 degrees. It also creates the same asymptotes for tangent, because tan is sine over cosine. And then the secant function bounces above the max values, just like cosecant, our last graph, and it bounces below to create that, I don't know, smiley face, frowny face. It just happens to be a 90-degree shift from each other, secant and cosecant, just as sine and cosine are the same graph, but they're shifted 90 degrees apart from each other. So now let's take a look at some more details about the graph of cosecant. So much like tan and cotan, the A value, or this thing here in red before the cosecant, doesn't really stand for amplitude, but it does affect these points here. So notice that the kind of smiley faces, the key point here is at 1, pi over 2 comma 1, and the little frowny face is at negative 1, 3 pi over 2 comma negative 1. So if I were to change that, it could move it up or down, depending on what the number is. And just like sine and cosine, cosecant, the standard period for that is 2 pi. And the domain is all real numbers except for wherever there's an asymptote. And remember, the asymptotes actually start at 0 and go every pi after that. As long as you don't change this number right here, that thing in blue, that will affect your frequency and will affect your period. So that means that one cycle is a smiley face and a frowny face. If you have a better name for both of those, you let me know. And the range is a little bit tricky, but if you have the graph, you can definitely figure it out. So it goes from negative infinity up until negative 1, includes negative 1, so there's a bracket. Picks back up at positive 1, includes that positive 1, and goes on to infinity. Now, if you change that 1, that red 1 in that quote-unquote amplitude spot, the negative 1 and the positive 1 will change, especially if you change the midline as well. But This is all standard stuff. So here's an example of a cosecant graph that is manipulated or transformed from having a 1 right here in red, which is the quote-unquote a value, and I'm going to change that to a positive 3. So notice that this point at 1 goes up to 3, but stays the same x value, still pi over 2. Same deal with the x value over here, still 3 pi over 2, but that negative 1 goes down to negative 3. And the asymptotes all stay the same. But things get a little bit trickier when we start messing around with the frequency and the period. So this is a typical one cycle graph of one cosecant of 1x, so standard cosecant. But then if I change that b value, that thing in blue, to 2, that means that I'm going to complete 2 cycles in a typical period where I would only complete 1 cycle. So I have twice the amount of frequency. So that's going to cut everything in half, meaning if my first asymptote is from 0 and then to pi, right, my first curve exists between those two, it's now going to exist between 0 and pi over 2, cutting that distance in half. So this pi over 2 point right here actually becomes pi over 4, so you also cut that in half. So remember, everything you manipulate to the x value essentially does the opposite of what you would normally think it would do. So although that looks like it's twice the amount, it actually cuts things in half. And you can even see that here, where the standard period is 2 pi, but I have to do 2 pi divided by b, and if b is 2, that becomes a period of just 1 pi. And so here's an example of taking the regular cosecant graph and keeping the quote-unquote amplitude the same, but changing that b value to be 1/4, or something much smaller than 1, but still positive. So remember, asymptotes go 0, pi, and 2 pi, but here you'd think, oh, I'll cut this into fourths, it'll become smaller. But remember, it's next to the x, so it's the exact opposite of what our intuition would tell us. So that's actually going to quadruple or multiply something by 4. So instead of going 0, pi, 2 pi for asymptotes, you're going to go 0, 4 pi, 8 pi. And this point, pi over 2 times 4 becomes 2 pi, and 3 pi over 2 times 4 becomes 6 pi. And if you like the algebra of it, right, standard period is 2 pi over 1, just 2 pi. But if I do 2 pi divided by b, which is 2 pi divided by 1/4, that becomes 2 pi times 4, or 8 pi. So it only completes 1/4 of a cycle in a typical 2 pi period. And of course, we can't forget what this graph will look like if I negate the a value here. So you probably already figured out what it's going to do. It turns this smiley face into a frown, same exact asymptotes, 0, pi, 2 pi, etc., except this point at pi over 2 becomes negative, and this point at 3 pi over 2 becomes positive, so it moves up there. Now let's talk about what a standard secant graph looks like, where the a and b values are both 1. Just like on the cosecant graph, there's no real amplitude here because this thing goes on to infinity and negative infinity in both y directions. And that a value, if you change it from 1, it changes in the same way that it did for cosecant. So if this changed to 3, each of these points right here would move up to 3, and each of these would move down to negative 3. Like I said, just like cosecant. The period here is also 2 pi, just like cosecant and sine and cosine. That shouldn't surprise you. And one cycle is a upwards curve or smiley face and one downwards curve with a smiley face. And there's an asymptote that splits that in half. So the distance here and the distance here is 1 pi each. But the thing that makes the secant graph a little bit trickier than a cosecant graph is that this first curve is split by the y-axis. Much like in our last video with tangent, that's split by the y-axis. I have to consider this distance of 1 pi and cut it in half to figure out what those first two asymptotes are. So half a pi this way and then half a pi that way. So that will change the domain. So remember I always start with the first positive asymptote, and then I add whatever the period is after that. So 1/2 plus 1 pi gives you 3/2 pi plus another one, etc. So your domain is x is an element of all real numbers except for wherever there's an asymptote, and that's how you express that, where n is an integer. and the range operates just the same based on this a value, just like it did with cosecant here with the -1 and the +1 in brackets. So really, the only difference between cosecant and secant is that 90-degree shift. So the last thing that we're going to do together is graph a function by hand. So let's graph one full cycle of this function here. So y equals -2 secant of 4x. And let's label all asymptotes and 2 key points in one cycle, and then we'll find the domain and range. So first thing I do is I identify my a and b values, and a here is -2. So normally that would take a point that's at y equals 1, move it up to 2, and do the same thing at -1 and move that down to -2. But the negative in this case is actually going to flip those curves over the x-axis. So normally there's a smiley face right here split by the y-axis, but that's actually going to flip and become a frowny face. So that means this function right here next to it, that curve, is going to be a smiley face instead of a frowny face, which it normally is. So keep in mind when you have a negative for an a value there, what that's really going to look like when you're done with your graph. And so the period is 2 pi over b, and 2 pi over 4 makes pi over 2. So let's start to mark up our graph here and go from there. So the y-axis you can label however you like. I like to skip by 2 if I have a lot of space, so I'm going to count by 1, 2, 3, etc. And just like the other trig functions when we're dealing with the x-axis, we want to split one cycle into 4 chunks. So that means 5 lines. So there's 1, 2, 3, 4, and I've spaced them out 2 each. You can do that however you like. So that means that this line right here and this line right here are going to be my first 2 asymptotes. So I'm going to put those in, and I'm going to finish out my 4 chunks over here, put in another asymptote. And remember, we're going to label the x-axis absolutely last. So here's what that's going to look like, and the only reason I have to split this in half is because I have a secant function, and it's not being shifted up or down or left or right, so it's just going to be half of a smiley face or frowny face that way, the other half there, and then a full frowny face or smiley face there. But I happen to know what's going to happen in each of these things, so I know that with that -2, we're going to make a frowny face here and a smiley face there. So let's graph that and label our x-axis. So here I've drawn in my curves. So remember, that's a downward facing one. That's going to start at -2. It's always smack dab in the middle between the 2 asymptotes. So right here, it's always going to be on the y-axis as long as you don't shift it left or right. And it's going to be at +2 in between these 2 asymptotes here, so on this middle notch. And the next thing I need to now figure out is what are the equations of my asymptotes, and then figuring out how to label my x-axis. So I figure this period is pi over 2. So that means from this asymptote all the way to this one is a length of pi over 2. So if I cut that in half, the distance between one asymptote to the next one is pi over 4, which is half of pi over 2. Now, that's great. I can count by pi over 4. But the only problem with secant is that the first curve here is split in half by the y-axis. So I have to take that length of pi over 4 and cut that in half. Make one negative, make one positive. So 1/2 of pi over 4 is pi over 8. So this first asymptote is x equals -pi over 8. And this first positive asymptote is x equals positive pi over 8. And then from there, I add pi over 4, because that's the distance from here to here. So pi over 8 plus pi over 4 is 3 pi over 8. You can thank your middle school math teacher for those fraction skills. And so now I have my 3 asymptotes here. And really, all I need to do is figure out what each of these notches is counting by and label. So first what I do here is I realize that if this is -pi over 8, that's pi over 8, and that's 3 pi over 8. Halfway between 0 and pi over 8, or -pi over 8, is a 16th. So I'm going to count by 16ths and just simplify the fractions as I go. So this is -2/16 pi, which is -1/8, -1 over 16, and then we get 0, 1/16, 2/16, which is pi over 8, 3/16, 4/16, pi over 4, 5/16, and then 6/16, which is 3 over 8, which is why we love to simplify fractions when we can. So that means that this point right here is 0, -2. That's one key point. The other one is at pi over 4. comma 2. So this thing is beautifully labeled. Beautifully is a stretch, but it's drawn, it's labeled, it's got everything that the directions are asking for. Now the last step is to find the domain and the range, and then we'll call it a day. All right, so the first thing that I do for domain and range is I look at my graph here and I think, okay, where's my first positive asymptote and how often is that asymptote repeating? So we always start the same way. X is an element of all real numbers, and X cannot be. And really you just fill in the two things I just said. You put in the first positive asymptote, which is pi over 8, and plus pi over 4, right? Because that's how often that thing repeats, because we got to take the period and cut that in half for a secant and a cosecant graph. So that becomes pi over 8 plus pi over 4n, where n is an integer. So that means that you start here and either 1/4 this way or 1/4 that way, however many times. That means that that is an asymptote. So x cannot occur there. And then for range, it's going to be negative infinity up to negative 2 inclusive, and then it starts back up at positive 2 and goes to positive infinity. And that's going to do it for this video. Thanks for watching.